Welcome back, everyone. Today, we're going to be taking a deep dive into the world of white dwarf stars.
Fascinating objects.
Yeah, and we've got a great resource to work with here. This recent scientific paper titled "An Observational Overview of White Dwarf Stars," and it really does cover a lot of ground. So I'm excited to kind of dig into this with you.
Absolutely. It's a very comprehensive overview.
Yeah, and it's amazing to think that these objects, these white dwarf stars, often no larger than Earth, contain a mass comparable to the sun.
It is really quite remarkable.
So, just understanding their formation and properties
Yeah.
offers a glimpse into the processes that really shape the universe as we know it.
Yes, absolutely.
So let's start there with that formation. The paper provides a really thorough overview of how these white dwarfs form. So,
Yeah.
so what's happening there?
Well, they begin as the core remnant of a star that has exhausted its nuclear fuel. And for stars less than about 10 times the mass of the sun, the cessation of nuclear fusion leads to the core's collapse under its own gravity.
All right, so it's a pretty dramatic end to a star's life, wouldn't you say?
Indeed, a very dramatic end.
But the collapse doesn't continue indefinitely, right?
No, it does not.
There's something that halts that, and that is what's known as electron degeneracy pressure.
Precisely.
And this is a quantum mechanical phenomenon, so it's pretty wild to think about.
It is.
So tell us about this electron degeneracy pressure. How does it work?
Well, it arises from the Pauli exclusion principle, which states that two electrons cannot occupy the same quantum state.
Right.
So as the core collapses and the electrons are squeezed closer and closer together, this principle forces them to resist further compression,
Uh-huh.
and that creates an outward pressure that counteracts the inward pull of gravity.
Wow, so it's this intense pressure that creates an object, you said, as small as Earth, but with a mass comparable to the sun. So just imagine the density of that.
It is mind-boggling.
Is mind-boggling. And the composition of these cores can vary depending on the mass of the progenitor star, right?
Right.
So what are some of the different compositions that we see?
Well, the most common composition is a mixture of carbon and oxygen.
Okay.
But some white dwarfs have helium cores, and the most massive ones can even have cores of oxygen, neon, and magnesium.
Wow. So the composition of the white dwarf can offer clues to the star's evolutionary history.
Absolutely.
But how do we even come to know about these stellar remnants in the first place? What's the history there?
Well, the first white dwarf, 40 Eridani b, was discovered by William Herschel back in 1785
Wow.
as part of a triple star system, but its true nature remained a mystery for quite some time.
That's interesting to think about those early astronomers grappling with these observations that just defied the known laws of physics at the time.
Yeah, it must have been quite perplexing for them.
Yeah, so what were they seeing that was so confusing?
Well, initially, these objects were classified as A-type stars because of their hydrogen-dominated spectra,
Okay.
but they were far too faint for their size, implying an impossibly high density.
Right, a real head scratcher, I'm sure. Yes, quite a puzzle.
So what was the key to solving this mystery?
Well, it was the development of quantum mechanics in the early 20th century.
Yeah.
And the concept of electron degeneracy pressure, which we just discussed, explained how these stars could be so dense, yet stable.
So advancements in theoretical physics really revolutionized our understanding of the cosmos in this case.
Very much so.
So we've talked about how they form and we've talked about how they were discovered. But how do we go about finding these white dwarfs amongst the billions of stars in our galaxy?
Well, they have unique characteristics that help us.
Okay.
They are often called white dwarfs, but they emit a lot of blue and ultraviolet light.
Uh-huh.
So early surveys like the Palomar Green survey were able to find them based on that property.
So they were looking for things that just didn't quite fit in
That's right.
with the normal stellar crowd.
Exactly.
And then the paper talks about the Sloan Digital Sky Survey. The SDSS really revolutionized the field.
It did.
So what did that survey contribute? Well, it was designed to study distant galaxies and quasars, but it ended up detecting tens of thousands of white dwarfs.
Really?
Because their colors resembled those of quasars.
Huh. So it was kind of a happy accident, a serendipitous discovery
It really was.
that greatly expanded our knowledge of white dwarfs.
Absolutely.
And then the Gaia Space Observatory has just really, it's hard to overstate how much that mission has revolutionized astronomy in general.
Yeah, it really has.
But specifically with white dwarfs too.
Yes.
So how has Gaia contributed to the study of white dwarfs?
Well, it can directly identify white dwarfs just based on their intrinsic faintness and their distance.
Wow.
And it has identified hundreds of thousands of white dwarf candidates.
it's incredible to think about. We've got this much more refined cosmic census now that allows us to pinpoint these faint objects with remarkable accuracy.
It's amazing.
It is amazing.
Yeah.
But, identifying them is just the first step. How do we delve deeper and unravel their individual secrets, so to speak?
Well, that's where spectroscopy comes in. By analyzing the light from these stars, we can unlock a wealth of information about their composition, their temperature, even the presence of magnetic fields.
It's like a cosmic fingerprint, revealing the star's hidden characteristics.
Very much so.
Yeah. And the paper goes into the different spectral types that are used to classify white dwarfs.
Yeah.
So let's talk about those a little bit.
Okay.
The most common type is the DA white dwarf.
Yes.
So what characterizes a DA white dwarf?
They exhibit strong hydrogen lines in their spectra.
Okay, so that means that their atmospheres are dominated by hydrogen.
Precisely.
And that makes sense because the heavier elements would sink towards the core due to that intense gravity.
That's right.
So it's like a cosmic sorting machine almost.
You could say that.
And then we've got the DB white dwarfs.
Yes.
What characterize them?
They exhibit neutral helium lines.
Okay, so their atmospheres are dominated by helium.
That's correct.
And then there are the DO white dwarfs.
Well, yes, they display ionized helium lines.
Okay, and then there are those with no prominent lines?
Yes, those are classified as DC white dwarfs.
Okay, and what does that tell us about their atmospheres?
Well, it suggests a lack of elements capable of producing strong spectral features.
So it's kind of a mystery what's going on in their atmospheres.
In a way, yes.
And then there are two more spectral types, right? DQ and DZ.
That's right.
So what are those all about?
Well, DQ white dwarfs show evidence of carbon in their spectra,
Okay.
potentially indicating that carbon has been dredged up from the core or perhaps even the result of stellar mergers.
Wow, that's incredible. And DZ white dwarfs.
Those are particularly interesting because they show the presence of metals in their atmospheres.
Metals? Now, wait a minute. Wouldn't those heavy elements sink to the core just like in the DA white dwarfs?
You would think so, but the presence of metals in DZ white dwarfs suggests ongoing accretion of material onto the star.
Accretion from, where could this be, remnants of planetary systems?
Exactly.
Wow.
Yeah.
So the white dwarf is slowly consuming the remnants of its former planetary system.
It seems so.
It's a glimpse into the fate of planets when their host star reaches the end of its life.
Yes, a rather sobering thought.
It is a sobering thought. But, spectroscopy also allows us to determine some crucial physical properties of the white dwarf itself.
That's right.
Like its temperature and its mass. So how do we extract that information from light?
Well, we use sophisticated models of white dwarf atmospheres to analyze the observed light.
Okay.
And by comparing the observed spectrum to these models, we can infer the temperature and the surface gravity of the white dwarf.
Okay. And how does surface gravity relate to mass?
Well, unlike normal stars, white dwarfs have a fairly straightforward mass-radius relationship.
Okay.
As a white dwarf's mass increases, its radius actually decreases.
So the more massive it is, the smaller it gets.
Precisely.
That's counterintuitive.
It is.
So by knowing the surface gravity, we can estimate its mass.
Yes.
What about temperatures? What kind of range of temperatures do we see in white dwarfs?
Well, they exhibit a wide range from a few thousand Kelvin to hundreds of thousands of Kelvin.
Wow, so the hotter ones are younger.
Yes, they've recently formed and they cool down over billions of years.
So the temperature distribution can tell us about the ages of the white dwarf population.
Absolutely.
And the paper also mentions something called a canonical mass.
Yes.
So what is that?
Well, it's the average mass of white dwarfs, which is about 0.6 solar masses.
Okay, and why is that the average?
Well, it reflects the fact that stars with masses similar to our sun have had enough time to evolve off the main sequence and form white dwarfs within the age of our galaxy.
So the majority of white dwarfs that we observe originate from stars similar in mass to our sun.
Precisely.
But they're also higher mass white dwarfs, right?
Yes, some resulting from the evolution of more massive stars and others potentially formed through stellar mergers.
Mergers, that sounds pretty dramatic.
It is.
And at the other end of the spectrum, we see a low mass tail in the distribution with some white dwarfs having masses less than 0.45 solar masses.
Yeah.
But how can such low mass white dwarfs exist? Because stars with masses low enough to form them haven't had enough time to evolve off the main sequence within the age of the universe?
That's a good question, and their existence points to enhanced mass loss, likely through interactions in binary systems.
Ah, so a companion star can influence a star's evolution, even determining its final fate as a white dwarf.
It can indeed.
Speaking of binary systems, the paper mentions that some white dwarfs have strong magnetic fields.
Yes, about 20% of them.
So tell us about these magnetic fields. How strong are we talking?
They range in strength from tens of thousands to millions of Gauss.
Millions of Gauss. That's astonishing, especially compared to Earth's magnetic field, which is less than 1 Gauss.
It is a huge difference.
So how do we even detect these fields?
We look for the Zeeman effect in their spectra.
And what is the Zeeman effect?
Well, strong magnetic fields cause splitting of spectral lines, and the degree of splitting reveals the strength of the field.
Ah, so it's like a magnifying glass allowing us to probe these incredibly powerful magnetic fields.
You could say that.
But what's the origin of these fields?
That's a question that is still under debate. Some scientists believe they are fossil fields, remnants of the original star's magnetic field amplified during core collapse.
Okay.
Others suggest they are generated during stellar mergers or perhaps even emerged during the white dwarf's cooling phase.
It's amazing how even these seemingly simple stellar remnants can possess such complex and fascinating properties.
They really are fascinating objects.
But we've only scratched the surface so far. We've discussed their formation, their identification, and some of their basic properties, but there's still so much more to explore. So let's continue our deep dive and delve into some of the more intricate aspects of white dwarf research, shall we?
Let's do that. We've discussed the density, the composition of white dwarf stars and how they're discovered and classified, and the evidence for planetary remnants surrounding some of them. But now let's turn our attention to a technique that allows us to probe beneath the surface and into the very heart of these stellar remnants, astroseismology.
Astroseismology, as I understand it, is the study of stellar pulsations.
Yes.
It's like listening to the star's heartbeat, revealing the processes that are occurring deep within.
Exactly.
But how do these pulsations manifest, and what can they tell us about white dwarfs?
Well, they manifest as subtle variations in the star's brightness over time. You can think of it as a gentle flickering caused by temperature fluctuations in the star's interior.
Okay.
And these fluctuations propagate through the star like seismic waves, carrying information about its internal structure, composition, energy transport mechanisms.
So by carefully analyzing these variations in brightness, we can glean insights into the hidden depths of the white dwarf.
Precisely, the patterns and frequencies of these pulsations act as a sort of stellar fingerprint, revealing the physical processes at play within the star.
And the paper mentions different classes of pulsating white dwarfs.
Yes.
Could you elaborate on these classes and what makes them distinct?
Certainly the most common class is the DAV, also known as ZZ Ceti stars. These white dwarfs have hydrogen-dominated atmospheres and pulsate due to the partial ionization of hydrogen in their interiors. As the white dwarf cools, hydrogen atoms begin to lose and regain electrons, changing the opacity of the stellar material and leading to these temperature fluctuations that drive the pulsations.
So it's like a delicate dance between atoms and electrons, a testament to the interplay of quantum mechanics and thermodynamics within the star.
A beautiful analogy.
Yeah. And then we have the DBV white dwarfs.
Yes.
Characterized by helium-dominated atmospheres.
That's right.
These pulsate at higher temperatures than DAVs,
They do.
with their pulsations driven by similar mechanisms involving helium ionization.
Exactly.
And at even higher temperatures, we find the DOVs, or GW stars,
Yes.
which pulsate with smaller amplitudes and longer periods.
That's right.
So each class occupies a specific instability strip on the temperature scale,
It does.
a range where conditions are favorable for certain types of pulsations to occur. And these instability strips provide a framework for understanding the underlying physics behind these stellar oscillations.
Yes.
By comparing the observed pulsations to theoretical models, we can determine the composition layering and even the physical state of the material deep within the white dwarf.
Exactly. It's like using an ultrasound to peer into the heart of the star.
It's amazing that we can glean such detailed information from something as seemingly simple as variations in brightness.
It is remarkable.
But I imagine there are still many unanswered questions in the realm of astroseismology,
Oh, of course, there are many mysteries yet to be solved.
such as,
Well, for instance, we still don't fully understand why DAV pulsations cease below a certain temperature, and the pulsation mechanisms of less common classes like hot DAVs and DQVs are still under investigation.
so each new discovery opens up a new avenue for exploration.
Very much so.
Speaking of new discoveries, the Gaia mission has revealed some intriguing substructures within the white dwarf cooling sequence.
It
The
has.
paper mentions the A, B, and Q branches. What do these branches represent, and what insights do they offer into white dwarf evolution?
Well, the white dwarf cooling sequence is a track on the Hertzsprung-Russell diagram
Right.
that maps the evolution of these stars as they cool and fade over billions of years.
Uh-huh.
And thanks to Gaia's precise measurements, we've discovered these distinct branches within the sequence, each seemingly corresponding to a slightly different evolutionary path.
Fascinating. Could you elaborate on each branch and its significance?
Certainly, the A branch appears to consist primarily of pure hydrogen white dwarfs, those with predominantly hydrogen in their atmospheres.
Okay.
This aligns with our understanding of their formation in the process of gravitational settling, where heavier elements sink towards the core.
Okay, and the B branch, how does it differ from the A branch?
Well, the B branch is thought to be populated by helium, white dwarfs, those with primarily helium in their atmospheres.
Okay.
However, what distinguishes them is the presence of trace amounts of hydrogen and carbon.
Trace amounts. Why would those be significant?
Well, these trace elements have a surprisingly large impact on the cooling rate,
Uh-huh.
shifting the helium white dwarf's positions on the Hertzsprung-Russell diagram and creating the observed gap between the branches.
Okay.
It demonstrates the subtle ways in which even small amounts of certain elements can influence a star's evolution.
And the Q branch, that one seems particularly intriguing.
Yes. The Q branch is perhaps the most perplexing of the three. It can't be explained solely by atmospheric composition. Instead, it appears to be caused by a remarkable phenomenon, crystallization of the white dwarf core.
Crystallization, you mean the core of the white dwarf actually freezes?
Exactly. As the core cools down, the ions within begin to arrange themselves into a crystalline lattice, much like water freezing into ice.
Wow.
This process releases latent heat, which slows down the cooling rate and leads to an accumulation of white dwarfs at the temperature range where crystallization occurs.
So the Q branch represents a sort of cosmic traffic jam with white dwarfs lingering at the crystallization temperature before continuing their slow fade into oblivion.
A vivid analogy.
Yeah. But crystallization alone doesn't fully explain the Q branch, does it?
That's right. Additional processes, such as the separation of carbon and oxygen within the crystallizing core, and potentially the distillation of neon, appear to contribute to the observed cooling delay.
It seems that even in their final stages, these stars continue to surprise us with their complexity.
Yeah, they do.
But we focus primarily on single white dwarfs. What about those that exist in binary systems?
Yes.
How do their interactions shape their evolution and give rise to even more exotic phenomena?
Binary white dwarf systems are indeed fascinating and crucial for understanding a wide range of astrophysical phenomena. They offer insights into binary star evolution, the progenitors of type Ia supernovae, and are even a source of gravitational waves. Their study provides a window into some of the most energetic and dynamic processes in the universe.
It's remarkable to think that these seemingly quiet stellar remnants can play such a dynamic role in the cosmos.
Indeed.
The paper mentions different types of binary systems.
Yes.
Could you elaborate on those?
Certainly, we can broadly classify them as single degenerate or double degenerate systems.
Okay.
In single degenerate systems, only one star is a white dwarf, while its companion can be a main sequence star, a giant star, or even a brown dwarf in double degenerate systems. Both stars are white dwarfs locked in a gravitational dance around each other.
A cosmic waltz of stellar remnants, and within these categories, there are detached and interacting systems.
Precisely.
Okay.
In detached systems, the stars are far enough apart that they don't interact significantly, however. In interacting systems, one or both stars can fill the Roche lobe.
Roche lobe, could you explain that concept?
The Roche lobe is the region around a star where its gravitational influence dominates. If a star expands beyond its Roche lobe material, can spill over onto its companion, leading to a range of interactions.
Yeah.
In interacting dwarf binary systems, this mass transfer can have dramatic consequences.
So in these interacting systems, the white dwarf can pull material from its companion, creating a dynamic and often violent environment.
Exactly.
And the methods for detecting these binary systems are just as diverse as the systems themselves.
They are.
We can observe them visually if they're far enough apart, like Sirius A and B.
Yes.
But for those that are too close together to be resolved visually, we rely on indirect methods.
That's right.
What kind of indirect methods are used to uncover these hidden companions?
We can use astrometry to detect wobbles in a star's position caused by an unseen companion. Photometric observations can reveal eclipses where one star passes in front of the other, causing a dip in brightness, and spectroscopic observations can detect Doppler shifts in the spectral lines, indicating the motion of a star due to the gravitational tug of its companion.
So it's like being a cosmic detective, piecing together clues to uncover the hidden partners in these stellar dances.
A very apt analogy.
And the paper mentions some truly exotic types of binary systems, like cataclysmic variables.
Ah,
Could you tell us more about these systems?
Cataclysmic variables are a fascinating class of binary systems where a white dwarf accretes material from its companion, often a main sequence star. This accretion process leads to dramatic outbursts in variability as the infalling material heats up and releases tremendous energy.
So these systems are anything but quiet and static.
Indeed, they are quite dynamic.
What are the different types of cataclysmic variables?
Well, there are several subtypes, each with its own distinctive behavior. Dwarf nova exhibit frequent outbursts driven by instabilities in the accretion disk surrounding the white dwarf.
Okay.
Nova-likes have high mass transfer rates, but no outbursts suggesting a more stable accretion process. And then there are the classical nova, where thermonuclear explosions on the white dwarf's surface create brilliant displays of light visible across vast cosmic distances.
It's amazing how these systems can vary so dramatically in their behavior.
It is.
And I imagine the presence of magnetic fields can further complicate the picture.
Of course, magnetic fields always add an extra layer of complexity.
So in some cataclysmic variables, the white dwarf's magnetic field disrupts the formation of an accretion disk, channeling the infalling material directly onto its magnetic poles.
That's right.
These systems are known as intermediate polars, or polars, depending on the strength and configuration of the magnetic field.
Exactly.
So the magnetic field acts like a cosmic funnel, guiding the flow of matter onto the white dwarf's surface.
A very good way to put it.
It's remarkable how these magnetic fields can shape the dynamics of these systems. And speaking of remarkable systems, the paper also mentions magnetic propellers and binary white dwarf pulsars.
Yes.
Could you tell us more about these exotic objects?
Certainly, magnetic propellers are systems where the white dwarf spins so rapidly that its magnetic field flings away the accreting material before it can reach the surface. It's like a cosmic windmill pushing back against the infalling gas.
A striking image. And what about binary white dwarf pulsars? How do they differ from traditional pulsars, which are neutron stars?
Well, in binary white dwarf pulsars, the interaction between the magnetic fields of the white dwarf and its companion, typically another white dwarf, produces pulses across the electromagnetic spectrum. These pulses are similar to those observed from neutron star pulsars, but the underlying mechanism is different.
It's fascinating how these systems, despite consisting of objects thought to be in their final stages of evolution, can exhibit such dynamic and energetic behavior.
It really challenges our preconceived notions about stellar evolution.
It challenges our assumptions about what it means for a star to be dead. But we've talked extensively about the stars themselves.
Yes.
What about their planetary systems?
Wow.
What happens to planets when their host star transitions into a white dwarf? It's a question with profound implications, not just for understanding planetary systems, but perhaps even for the possibility of life beyond Earth.
It is a question that sparks a lot of curiosity and speculation. As a star evolves into a white dwarf, its planetary system undergoes a pretty profound transformation, a story of survival, destruction, and perhaps even renewal.
The paper highlights that planets close to the star are unlikely to survive this transition.
Yeah, during the star's red giant phase, its outer layers expand dramatically, engulfing and incinerating any planets orbiting within a few astronomical units, so that the inner solar system, once teeming with planets, would be effectively sterilized.
A rather sobering thought. But what about planets farther out? Do they stand a chance of surviving this cosmic upheaval?
Planets in the outer regions of the system might survive the red giant phase, though their orbits would likely be significantly perturbed by the shifting gravitational landscape. It's a cosmic reshuffling, with planets potentially scattered inward or outward, their fates hanging in the balance.
So while some planets might meet a fiery end, others can find themselves on new and unexpected trajectories. And the paper mentions evidence for planetary debris around white dwarfs, suggesting that not all planets escape unscathed.
Right. We see this evidence in the form of metal pollution in the white dwarf's atmosphere. These metals, heavier elements like calcium, magnesium, iron, and sodium, are indicative of rocky material accreting onto the star.
And the composition of this accreted material closely resembles that of rocky planets, asteroids, and comets, suggesting a link to planetary remnants.
Exactly. The white dwarf acts like a cosmic graveyard, slowly accumulating the remnants of its former planetary system. a testament to the dynamic and often destructive processes that shape stellar systems.
It's a sobering thought, but also a fascinating glimpse into the long-term evolution of planetary systems. But this evidence of planetary debris isn't limited to spectral analysis, is it? The paper mentions other observational clues.
You're right. In some white dwarf systems, we observe transits, periodic dips in brightness caused by material passing in front of the star. These transiting objects are likely remnants of planets or asteroids fragmented and scattered during the tumultuous transition to the white dwarf stage.
And the paper highlights a particularly compelling case. WD1145 plus 01 is seen, the first white dwarf system where transits from multiple debris objects were observed.
WD145 plus 01 is seen as a remarkable system. It not only exhibits transits, but also shows an infrared excess, indicating the presence of a dusty debris disk surrounding the white dwarf.
So a ring of dust and debris, perhaps the remnants of a shattered asteroid belt, orbiting this stellar remnant. It paints a vivid picture of the aftermath of a star's death throes.
Indeed. And in some systems, we observe metallic emission lines suggesting the presence of a gaseous debris disk likely formed through collisions within the debris cloud. Each observation adds another layer to our understanding of these dynamic environments.
It's like a cosmic archaeology, piecing together the history of these planetary systems from the fragmented remnants they leave behind. But directly detecting intact planets around white dwarfs is a much more challenging task, isn't it?
It is. The traditional methods for exoplanet detection, such as transits and radial velocity measurements, are less effective for white dwarfs. Their small size and faintness make transits difficult to detect, and the broadness of their spectral lines makes radial velocity measurements less precise.
But despite these challenges, a few planets have been found orbiting white dwarfs, testament to the perseverance of astronomers and the ingenuity of their techniques.
Yes, a handful of planets have been detected using various methods, including pulsar timing, direct imaging, and microlensing. These discoveries demonstrate that planets can survive the dramatic transition to a white dwarf stage, though their existence likely depends on a delicate balance of factors.
It's remarkable to think that planets could endure such a tumultuous journey and find themselves orbiting a stellar remnant. It raises fascinating questions about the long-term habitability of planets and the possibility of life persisting in such environments.
Indeed, it's a realm ripe for exploration and discovery, pushing the boundaries of our understanding of planetary systems and the potential for life beyond Earth. But to gain a truly comprehensive view of white dwarfs and their place in the cosmic landscape, we need to consider the broader population, not just individual systems.
The paper emphasizes the importance of volume-limited samples in studying the white dwarf population. Could you elaborate on why these samples are so crucial?
Volume-limited samples select stars based on their distance from Earth rather than their brightness. This approach helps to avoid biases inherent in magnitude-limited surveys, which tend to favor brighter objects. Volume-limited samples provide a more representative snapshot of the true white dwarf population, allowing us to draw more accurate conclusions about their properties and distribution.
So it's like taking a census of all white dwarfs within a certain volume of space, regardless of their luminosity, ensuring a more accurate representation of the overall population.
Precisely. And one of the most comprehensive volume-limited samples to date is the 40-parsec sample compiled using data from the Gaia mission. This sample, containing over 1,000 white dwarfs, has provided valuable insights into their diversity and characteristics.
What are some of the key findings from this 40-parsec sample?
The sample confirms that DA and DC spectral types are the most common with DA white dwarfs, those dominated by hydrogen in their atmospheres, comprising over 60% of the population.
So hydrogen-rich white dwarfs are the norm, as we might expect from our understanding of stellar evolution.
Yes. The sample also reveals that about 11% of white dwarfs show signs of metal pollution, indicating the presence of accreted planetary debris. This finding underscores the prevalence of planetary systems and the significant role they play in shaping the evolution of white dwarfs.
It's a reminder that these stellar remnants are not isolated objects, but often surrounded by the remnants of their former planetary companions. And the sample provides further evidence that about 20% of white dwarfs are found in binary systems, highlighting the importance of binary interactions in their evolution.
Indeed, these findings from the 40-parsec sample offer a glimpse into the broader population of white dwarfs in our galaxy, but this is just the beginning. The future of white dwarf research is incredibly bright, with upcoming large-scale surveys and new space telescopes poised to revolutionize our understanding of these fascinating objects.
It's exciting to think about the wealth of data and discoveries that await us. What are some of the most promising avenues for future research?
We have upcoming large-scale spectroscopic surveys like SDSV, DCI foremost, and WEAVE, which will increase the number of spectroscopically confirmed white dwarfs by an order of magnitude. These surveys will provide an unprecedented level of detail about their spectral properties, allowing us to probe their compositions, temperatures, and magnetic fields with greater precision than ever before.
So a dramatic leap forward in our understanding of the diversity and characteristics of white dwarfs.
Exactly. And we have new space telescopes like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, which will provide unparalleled photometric data, allowing us to study fainter white dwarfs in more distant regions of our galaxy. These telescopes will open up new frontiers in white dwarf research, allowing us to explore their populations, their environments, and their interactions with other objects in unprecedented detail.
It's an incredible time to be studying white dwarfs. These seemingly simple stellar remnants are proving to be far more complex and dynamic than we ever imagined.
They are indeed. And perhaps most excitingly, we have the LISA mission, a space-based gravitational wave observatory, which will be able to directly detect gravitational waves from merging white dwarf binaries.
That's a game changer. It will provide a completely new way to study these systems, allowing us to probe their masses, orbital parameters, and the physics of their mergers in ways that were previously impossible.
Precisely. LISA will usher in a new era of white dwarf research, providing a window into the most extreme environments in the universe and allowing us to test our understanding of gravity in ways never before imagined.
So as we conclude our deep dive into the world of white dwarf stars, we're left with a sense of awe and wonder. These tiny fading embers of stars, once thought to be simply the endpoints of stellar evolution, are proving to be dynamic, complex, and full of surprises.
They offer insights into stellar evolution, planetary systems, and fundamental physics. They challenge our assumptions about the nature of stars and the potential for life beyond Earth, and they beckon us to explore further, to delve deeper into the mysteries of the cosmos.
Indeed, white dwarf stars, these seemingly unassuming objects, are a testament to the endless wonders of the universe, reminding us that there's always more to discover, more to understand, and more to marvel at.